Welcome to the Brainstorm with Sparks and Finn, a podcast where we brainstorm the science and philosophy of a new age, an electric universe age, and what it means for the human race, past, present, and future. I'm Finn.
And I'm Sparks.
And today we're busting into the mainstream party. Hey, you can't come in here. This lecture's on the Big Bang.
Oh, you haven't heard. Here, read this. Space is electric.
It's electric.
Today's guest, better hold on to your hats, people, because we're not worthy.
We gotta get going.
No. Stick around. Hang out with us.
Cool. Yeah, we'll stay and hang out with you. With Gareth Samuel.
We're not worthy. We're not worthy. We're scum. We suck.
The Ayatollah of alternative cosmology, who's come across a foundational law that changes everything. Buckle up, because today we're talking about Ampere's missing law. OMG.
I'm just gonna
Hi,
hit.
Gareth. I'm geeking out. It's great to meet you at last. I love your stuff, man. The See the Pattern shows are just phenomenal. You have been on a run, my friend. These last few have been mind-blowing, like all
Fire.
Yeah. So that's why we dragged you onto the Brainstorm. I'm Matt, that's Sparks.
Exactly.
Ampere's law.
Ampere's law.
Yeah, I didn't even know about it until I went to the conference. So it was at the conference I met Andreas Cees and yeah. And he was talking about it. And, you know, at first I was like, that doesn't make an awful lot of sense. Like, why would we have ignored something so fundamental that actually changes the way you look at things? So I was like, okay, you know, that sort of makes sense. And then I started reading the papers, and the more I sort of dug into it, the more I'm kind of like, yeah, I think this is not just one of those niche sort of sounds cool, people do experiments on it, and you know, it's a maybe if, but actually the fact that Maxwell was so gushing about the work that Ampere did in terms of the quality of his work showed that there is something to what he discovered, and that forgotten thing is essentially an abstraction that we use, which we call the magnetic field. But really it's the same force, and when you look at that you kind of go, that it makes so much more sense. You know, it seems so much more logical if it's all the same thing. I mean, sure, we sort of abstract away and say, you know, a moving charge creates a magnetic field, but we never really sort of explain why. I know I've seen other people explaining it in terms of, you know, when you look at how the field propagates and creates, you know, a ripple, and that the ripple then becomes the magnetic field. But I think when you look at Ampere's view of it, it kind of makes sense. The problem is when you look at Ampere's view, you have to understand and accept that this is instantaneous action at a distance. There's no field. And kind of part of that you go, yeah, well, actually a field is just an abstraction anyway. But then you kind of go, well, that changes everything. It changes the way you look at all forces. I mean, sure, he did it for just the moving electric charges, essentially. But why wouldn't that same idea apply to everything else? Of course, in his day, that's what they believed. You know, gravity was an instantaneous action at a distance. Now, obviously, some of it you can say we can measure the speed at which fields propagate, and that propagates at the speed of light. But even there, you look at what Kirchhoff did, and his analysis of essentially what Ampere's work was, and which showed that actually that cascade effect, which is difficult to animate. I tried my best to try and explain what it is, but it's essentially the fact that if you have a whole line of these charges, each the first charge, if you move it, instantaneously acts on all the particles in the chain instantly. And obviously the size of the force falls off with 1/r², the normal sort of inverse square law you would expect. But of course, as soon as the first one starts interacting with the second one is moving. Now the second one does the same thing for all of those in the next chain. So you end up with this like cascade effect, and it's that cascade, the fact that essentially you're assuming that there is some sort of lag, some delay in terms of each particle receiving, accepting, and then doing its thing, which creates this delay effect.
Okay, so
which is why galaxies are spiral.
Well, galaxies are spiral. I mean, there are many different ways to explain why galaxies are spiral.
Sorry, Ben.
No, right. Let me go back to that because I have had that video of yours on repeat for like the last 24 hours. I went to bed with it. I woke up with it, trying to wrap my head around it. Tell me again how you can have an instantaneous. It's not an instantaneous reaction. You said that that every particle along that chain not feels the force, but how is that instantaneously connected? Because you said that there's action that slowly moves. What is the thing that's instantaneous?
The force. So essentially, if you move the first particle, so you're ignoring how you moved it, but the particle is moving, so it's moving closer to the ones in front of it. Yeah, so let's a really simple case where you're just assuming that they're stationary, but obviously Ampere's law is for motion, but just to understand the concept. So if I move the first charge towards the chain of charges, that movement means it's closer to the next charge. So therefore, this charge now starts to experience an increase in force. That increase in force is essentially instantaneous across the entire chain. But obviously, the further down the chain you go, the smaller that amount that they feel is. Yeah?
Like a daisy chain, more or less.
Like a daisy chain, yes. Yes.
Right, and it's daisy chaining, but and that's the thing is a daisy chain. When you look at a daisy chain happening, at least maybe I'm misunderstanding this, is you have one thing happen, then another thing, then another thing, and another thing. That's a completely different concept than instantaneous. You would not have one thing happen right after another.
You have to imagine that along the chain, essentially that's the first line that I draw where you have all the sticks in a line.
Right.
And then as the first stick starts to move, they all start to move, but they're moving with decreasing amounts.
Decreasing,
okay?
Yes, they attenuate.
Yeah, the amount that they decrease by goes down exponentially. Yeah. The 1 over r squared is the sum of all the interactions when you then take the second order, the third order, and the fourth order together. So the second order is the fact that the first one has moved, caused the second one to move, and so therefore it's the movement of the second one we're now looking at along that entire chain. It's essentially what you would see as the field building, the field propagating through space, is that building of the maximum value of the field as it moves outwards, because each one you're summing together, each movement, third order, fourth order, fifth order, sixth order. Obviously, by the time you get to the end of the chain, the movement and the amount is you can't even measure it.
Right, it's attenuated. Okay, I'm sorry. I think I see the problem here. I'm assuming that one little stick is moving, then the next little stick, but they're all moving together, right?
Yes.
That's what I missed.
Yes.
Okay. I was thinking that it was sequential, and it's not. They're all, and of course it would attenuate. Yes, the 1 over r squared, got it. Okay.
Yeah.
Kind of like yanking on a bungee cord or something. Like you get the initial force right away, but it's elastic, and the end doesn't quite catch it as much. Like the energy slows down as it gets away from the source.
Yeah.
It's not it slows down; it attenuates.
Yes, indeed, it attenuates. There's effectively you have a lag that's introduced because of the interaction with each particle. You have to assume that each particle has, let's just say, a processing time where it then, and it's not quite like that, but that's essentially how you can visualize the chain, effectively like creating a wave. Like if you read Kirchhoff's paper, it's clear in terms of the maths. I mean, it's a math-based solution that he obviously goes for rather than an explanation one, which is what I prefer, a visual sort of explanation of it rather than a mathematical. I mean, it obviously has to be mathematically sound,
Would it be like a pool ball smashing into a line of other balls and each one reduces in? No? Okay.
No, 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 no. It's almost like you'd almost. The thing is, you have to separate it into different layers because you have to imagine that all the balls are connected directly. So as soon as you move the first ball, they all feel the force,
At the
but
same
not the
time.
same amount at the same time, but not the same amount of force.
Not the
It's
same
a
amount.
reducing.
Mm.
But the second ball, when it moves, it also then does the same thing for the third, fourth, fifth, sixth, and then the third on the. So there's a cascade effect, and that cascade effect.
Oh, I got it.
Yeah,
Okay,
yeah.
okay, okay. So it is almost like instantaneous information transference because
Yes,
they're okay.
yes.
It is.
And that's why the whole coming back to maths principle is important, because if you consider that the universe is indeed composed of filaments that carry charge, then that has very specific implications for how things are connected to one another in a
Yeah.
very different way than essentially I ever thought about until you think about this. And it makes maths principle so much more real, I think. Like, because a lot of people say, well, it's just not maths principles nonsense. How can everything be connected? How can the entire mass of the universe, the inertia of the universe, talk to every other part of the universe? It doesn't make any sense. No, but maybe that's a sign that actually the way that we've developed our physics and our equations has been down a particular route of fields that somehow removes that requirement for instantaneous action at a distance.
Right.
But
Yeah,
Sorry, Matt, go ahead.
go ahead. It's like the mainstream has devised ways to describe things and then put rules of physics that are attached to those descriptions, like magnetic field lines, like the strong force, things like that.
I think if you look at why we've ended up with fields, it's an understandable reason. Like the idea behind it is to try and visualize and simplify what you can deal with. And it kind of makes sense, and it does. It's not that it doesn't work; it does work, but it's the edge cases that, in particular, when you look at Ampere's law, that it highlights that actually those don't work in every situation. You know, that he clearly identified certain scenarios where actually you would expect things to occur that the field-based approach wouldn't,
Right.
and that's important because that's showing that actually there is fundamentally something missing. Okay, in everyday life, you probably never come across those edge cases, but
Right.
that doesn't mean it isn't important, because particularly when we're talking about something the scale of the universe, then actually things become very important.
Absolutely. So, and
What do you
this
got
is where
there?
I think it can be a little bit confusing, because when you start to consider that maybe fields are not the way the universe is structured, then that, for people like me who have magnets and love to play with magnets, when you get them close like this, you feel something, and trying to say that that's not a field effect is a little bit counterintuitive. So what would Ampere say, do you think, that's going on here with this attractive field? I mean, you can see me sitting here playing with it, and this is obviously the attractive side. How does Ampere's understanding tell us that that's not a field?
I think you have to go beyond Ampere to start understanding how, because he never really looked at magnets in particular. So you won't find the answers to those questions there. But I think that the reality is that what you're dealing with in terms of magnetic fields is no different to essentially what Ampere is describing in his equations. You just have to consider how are the charges moving in those scenarios that create the same effects that we see. I mean, it's the same way that how do we explain magnetic fields in a magnet nowadays? You know, it's about the domains and how the electrons move and making sure that they all align with each other, that then creates this strong magnetic field because they're all adding together. And that's no different to explaining it in Ampere's view, in my view, anyway.
Sure. So I guess the thing, and I think when I first was old enough to understand magnets and to think about them coherently, is and this is the question, and maybe the question is wrong by itself, but my question was, what is the thing that is causing the attraction? Because there's, with your little stick analogy where everything is connected and they all move together, we can't tell, and macroscopically, there's no thing that's connected here that's causing that attraction.
But the same also applies to, like, when you take your jumper off and you get a highly statically charged jumper. You can feel that, you can feel the hairs on your skin start to stand up. That's the same thing. There's a force that is acting that you can't see, you don't know the origin of. I mean, we know that obviously it's to do with the transfer of electrons and actually that's it. Well, it's funny because Andre Assis also pointed out in a discussion that we were having that essentially that is also a massive misunderstanding. That the whole thing about how
Really?
Yeah. He was mentioning, and I need to look it up. It's probably on his website. He's got lots of papers on it. But he was mentioning that there's a guy who did more recently, experiments on how charge is transferred, and because often the way that we teach there, it's electrons that transfer. Depending on the material, you've got an electron donor or one that wants to take electrons. But he said that this guy had done these experiments, and actually, in a lot of the materials, that's not actually the case. It's parts of the polymer that are being pulled off that have either a positive charge or a negative charge that are being deposited on the other material. It's still a charge-based difference, but it's not necessarily always just electrons. There are other chemicals that are involved in that transfer process. And that's fascinating. That's because that's not the way we teach it. We teach it very much as an electron thing. But actually, it's not. There are bits that break off of these, rods that we rub. I mean, sure, in a metals case, yeah, it's electrons. You can't really argue it. But the plastics that we use, it's not really that clear cut. There are chunks of plastics that get pulled off that retain part of the charge, and sometimes they're more positively charged and sometimes they're more negatively charged.
Oh, okay.
And they get deposited on. Yeah,
well,
they're still obviously.
If you're going to go down that road, then that immediately makes me think of Ito Call's SAM model, where the nucleus builds at sites. I forget exactly what he calls it, but sites. But some of those sites are positively charged. It's not just electrons and electron flow. It's a positively charged site, and then bloop, you get an addition. And that sounds to me like exactly what this guy is doing. I'm sorry.
He was a chemist, and I don't know whether he was in the field of organic chemistry or non-organic chemistry. I'm not entirely sure, but he was doing experiments on trying to understand the chemical properties of the rods and identifying that when you rub from one material to the other, what exactly was being transferred. And it's not quite like the SAM model in that respect. You're basically talking about, I mean, obviously in a lot of these plastics, they're long polymers. And essentially when you're rubbing it, sometimes some of the polymers break off, and it's those lumps. Now I haven't read his paper, so I don't know. This is purely from what Andre was telling me. And that was news to me. Like the first time I heard it, when he was explaining that, I was like, what? That doesn't make any sense. That was in the, I don't know if you've seen the clip yeah, exactly like that. Yeah, that's the idea. And he looked at, there are certain chemicals that are more favorable to doing that than others. So when we talk about certain materials being donors or givers of, electrons is what we think is being transferred. Actually, that's not always the case. It's to do with the chemical composition and what happens with it. Yeah, obviously we tell the story and it's a convenient story we tell. But like he got us to do, I recorded the bit and I uploaded it on my Patreon, where he ran through some of those experiments. and I don't know whether I got all of it, but he basically asked us to predict. Like he had different materials and he'd rub them, and he asked us to predict whether you think it would be positive or a negative charge. It was extremely difficult. Like really,
Really?
I was guessing most of the time, and most of the time he was like, "Nope, that's not right." And yeah, it like because you assume it's just this well-known thing,
Yeah.
and
You
it's
would
not. But
think.
yeah, you would
Okay,
think.
Matt, hold the phone. I got to walk over to my lab and grab something because I've got an example, Gareth, of exactly what you just said. So, Matt, say something.
Okay.
Yeah.
Shit!
I'm
Whoa!
convinced that.
Holy crap!
You okay there, Sparks?
Wow! Apparently my transformer has been on. Jiminy crap! I just got hit with 12,000 volts. Woo!
Are you feeling
Holy
good now?
crap! It
Mad
usually
scientist
hums.
lab.
I can usually hear it. I had no idea that was on.
Are you creating Frankenstein over there?
Wow!
Yeah.
My God.
I was doing some
Frankenstein was the doctor.
Right.
Yeah, Frankenstein's monster, to be technically correct. Okay. Wow, that was fun.
And all
That's
for
twice
these
in-
6.
Yeah, twice in 2 days. We'll have to beep that out. Anyway,
Look what
You
he does
said
for the art.
that was not on purpose. That scared the crap out of me. This is a barbecue skewer, that bamboo skewer, right? For making shish kebabs. This is what I use to
Yeah.
touch my transformer so I don't do what I just did. And this is a plastic rod. Okay. So I had my transformer connected to a bead chain, just a bunch of beads forming a chain. And I held this in
beads.
my hand and I brought it close to it and it did this. It was actually
Yeah.
attracted to it, just like the example what you said. So then I'm thinking, that's weird. That's bamboo. I don't usually associate wood or bamboo with charge. Then I take the plastic rod, which we always associate that, and it did this. And if you don't see it moving, it's because it didn't move. And so
Yep.
then I did this.
Huh.
And I got a tiny little bit of movement. So yes, when he said that you don't expect that different things have different charges, yeah, I just did it. And that's
Yeah.
absolutely right.
So by infusing something with charge, you can get it to be attracted to the whatever the attractive force in the area is. Does that kind of explain gravity as an electrostatic effect, where we are filled with the Earth's charge and therefore we are attracted to the Earth?
I'm not convinced by the idea of electrogravity. I mean, I've looked at it, but no, at the moment I don't see it. It would be too complicated for it to work on the scale of for example, a solar system, unless you invoke some other thing that drives. Like I get the idea of it. Like if you were to look at the solar system or another body, you can assume like a motor effect. Like it's an easy. The problem is the motor effect doesn't create the motion that we see in terms of Kepler's law as you move further out. So you have to have some other way of being able to alter how the rotation then happens. And I think also if you considered an electrogravity, the problem is that in my mind, gravity is a singular force. It acts in one direction. Like we haven't discovered anti-gravity. If we
Push
did,
gravity.
then maybe. Well, no, but push gravity is just a way of as an alternative. I like the idea of push gravity, and by push gravity I mean the Lesage push gravity. So the idea that actually the force isn't an attractive force; it is a force that we see because of the movement of an ether that pushes on everything else, and it's the absence of that creates the effect of gravity that we perceive.
Like a pressurized bubble being squeezed in by interstellar space.
Yeah, exactly. There's some outward pressure that creates
and that pushes us into the surface of Earth by pushing our atmosphere.
Sort of, yes. The Lesage model which has problems. I'm not going to say it's a perfect model, but the idea is you have these very small particles that travel at many times the speed of light, that effectively are all around us, and it's the essentially when they bounce off you, it creates a reaction force. Yeah, so that sort of pushes on you. But so if you had them on all in equilibrium, there'd be no difference. You wouldn't feel any particular force in any direction. But as soon as you have exactly, you shield it. So the idea is that in a massive body, those particles can only penetrate a certain distance. So like a moon or a planet shields the other side. So if you have a planet and a moon, it'll shield the moon side. If you imagine them all around, it creates like this shadow zone, and that shadow zone creates an inward pressure. That's the idea of a push gravity.
You addressed this in one of your videos a few years ago, very specifically. And
Yeah.
you did, Gareth, you did the one thing that no other human has done. You picked up on, and I really appreciate it. And I think I sent you an email at the time when you did this. You picked up on Wall Thornhill's, and I know we're talking against Wall. Don't burn us here. But you picked up on one of Wall's faux pas that he said in one of his presentations. How that the elements, these microscopic particles that create gravity felt the gravitational field. And we're like, and I heard that, and my ADHD immediately kicked in and said, no, they are generating that. They can't feel the thing that they're generating. And you caught, what just happened? No. Can you guys see this little notice that just popped up on the screen?
No, it's a notice just for you.
Oh, goody.
CIA's coming.
Anyway, okay,
Yeah,
it just says that our
10
meeting is, for some reason, okay, apparently our technical glitches are continuing. It says that our meeting's going to end in 10 minutes because apparently I'm not on the pro version, which is stupid because I've always been on the pro version.
Bluffing.
Yeah. Anyway, Gareth, you said that. I'll fix this in a second. Jeez. You pointed that out. You picked that out from his video too, and I really appreciate that you did that. You pointed it out, you said it, and you explained it. That was really good.
Well, in all the dealings I had with Woll, that was often a point that we'd come back on, and it's kind of unfortunate because the last video that I was working on for the Thunderbolts was a video about Schultz's star, I think is what it. I can't remember what the end title was, but it's the idea that this star that approached the solar system, I want to say 80 million years ago, something like that, and then deflected off. And there is it's a mainstream sort of idea that they can see the direction of this star, and based on the current direction, they sort of can work out that it must have been really close to our solar system 80,000 years ago. So it's like a near miss, essentially, is the idea. And I got the idea, well, that maybe is an interesting story to do because it tells potentially is evidence of what the Thunderbolts often talk about capturing other stars. So I was interested in doing it. But Wall wanted to put in, he wanted to include electrogravity, and I was like, no, I'm not. Like unless you can convince me that it makes sense, I'm not going to put it in. And he was like, okay, well let's see if we can set some time aside and go through it. And unfortunately, from that point on is when he became more and more ill. So there are bits that he discussed with me, but I think by the time he was then discussing with me, it part of it became fragmented. Like some of it didn't make sense in its entirety. But one of the things that I do remember him saying was this idea, because he remembered me picking up on that point, and he was like, yeah, I know, I made a mistake. I shouldn't have said that. And one of the things that which doesn't entirely work, but his explanation for what he meant, but it didn't come out right, was essentially in his mind, when let's say a pinch is created and a new star is being formed, that the intense electric field at that point creates an imprint on the I forget what he called the little particles. He had a name for
Oh,
them.
neutrinos?
No, 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 no. No, it wasn't. It wasn't his name. It came from someone else who he quoted, who'd come up with that concept. But anyway, the subparticles that he thinks the
Oh,
electron and proton are made up of. But anyway,
um,
it's sort of irrelevant. He saw that that initial pinch created a sort of a dipole that they somehow remembered, and then that's the effect that then triggers. So
oh,
different star systems would be born with different. But the problem is that that doesn't. Although you kind of go
it's too
that
simplistic.
okay. Well, also, why wouldn't it? Why would the dipole remain? And because again, the idea is also that that can change. So if it can change, what conditions change it? Like
Right,
it
exactly.
was a better explanation, but it still, in my mind, doesn't
It
entirely
was like a
work.
stepping stone. It's like the first step. I mean, it clearly can't be the entire picture, but it opens up channels to progress and discover,
Well, I think if you think of it,
hopefully.
because part of the problem I see with an electrogravity model in the way that he was describing it, which is kind of a dipole offset, is you always end up with a positive and a negative, which can create some really difficult balancing acts that we don't necessarily see when we look at normal gravity systems. But if you consider like Ampere's law and the way that in essentially you create two forces from the same force, although in his mind they're all the same force, but essentially a pushing and a pulling can occur because of the same force and they're all moving in the same direction. And I wonder whether the same might be true of gravity, that essentially what we're seeing is a one directional force, which is the result of something else.
I agree.
And I don't necessarily think that it's to do with electric charges, but they may have an involvement in it. But
What if we come to find out that the electric charges are secondary to a primal
yeah,
force? That ah,
well, I mean, yeah, I mean, then the question is, what is? Because the weird
what
thing
is
when you
that?
look at charge, yeah, but when you look at charge, right, the two units of charge that we have are so different, and that's a strange thing. You know, you've got the proton and the electron, two very different sizes, and yet the same charge, exactly the same, I mean, exactly the same charge, and that.
That's weird.
Well, that is weird, but that to me almost says they are really the same thing. I think Ido had this idea, which I quite like, which is essentially that they're pulled apart. That they started as one thing, and you pull them apart, and they always want to be together, but actually they come from the same thing. More as a philosophical discussion than a necessarily rooted
Charge
in.
separation makes it kind of sad, really.
Yeah, but the fact, and what's even sadder is they never actually. You can never get an even if you brought an
It's
electron up to a proton. What would it do? Like it
it's
doesn't. It's not like it goes back into
Oh,
its primal state. It just they always want
they'd,
to be somewhere, but they can never get there.
they'd probably
oh
argue all the
man,
time and then get a divorce.
Yeah,
a cosmic nuclear Romeo and Juliet. They
yeah.
love each other. They can never
Lady
be
Hawk.
together.
Played out on different levels. You've got the atomic levels, or the shell atom shell level, and then you've got the nuclear electrons in the SAM model, and then maybe you've also got free electrons. But like, how free is a free electron?
Right, right.
I don't know.
I mean,
Like, I don't,
How free are any of us?
how free? I knew you were
never.
going to say that. I knew you were going to say that.
I'm a predictable creature.
Okay,
Less and
kids,
less
hold on.
free every day.
Right. Time out. For some reason, my Zoom is telling us that it's going to end this lovely conversation in 2 minutes and 25 seconds unless I upgrade. Now, the problem with that
That's
is I have
extortion.
upgraded and I don't know why it didn't let me log into my upgraded Zoom chat. So I'm going to hit a blue button right here, which is going to allow me hopefully to go into the upgraded section, or it might just cancel us all. So hold
All
on to
right.
if it cancels us all, let's get
Okay.
on our social media and communicate. Let me see what happens here.
Sounds good.
I just hit it and nothing happened.
We're still in business.
We're still in business, but we've only got 1 minute and 45 seconds left.
Well, can I fill that with some stupidity?
Yes, please.
If gravity is not electromagnetic, then how do we explain plant and animal giganticism? So in the proto-Saturn theory, we're around a smaller sun. We're getting less electrical input into the Earth, and therefore we have less gravity and things get bigger. Now that we have the sun as our source of input, nothing gets bigger than an elephant on land and a blue whale in the water. So is this an argument for electrical gravity, or does the standard model of gravity explain that too?
No, I don't think the standard model of gravity. Like I've never seen a good explanation as to the, other than that some of these dinosaurs possibly roamed in water and not on land. I mean, that's possible. I'm not sure that necessarily accounts for all of them.
Matt,
I'm still.
We're going to be unceremoniously disconnected any second now.
All right.
So
pterodactyls for 400 pounds.
Okay, let's reconvene on our apps and communicate when we can finish this conversation.
All right.
Oh, and there.
A few moments later.
I'm gonna hit. All right. 40 minutes. Here we go. Okay, Matt, hurry up.
Let's go.
I loved my conversations with Wall. Oh, there he is. And was just devastated when I got the news that he had passed on.
Yeah. I mean, I kind of, if I'd have known, but I kind of understand why you wouldn't tell anyone. But because the last time I spoke to him was probably sometime, I think it was in December, maybe late November, early December, I think. And then he obviously died. I think it was January, wasn't it?
I think it was in March. It was early year. Yeah.
Was it March? Yeah. Well, but anyway, it was. If I'd have known at the time, I'd have. I mean, I don't know how you'd have done it differently, but it was just. You kind of look back and go, well, I wish I'd have done that conversation differently, you know. But yeah,
tough stuff.
It is. Yeah. Yeah, and it's a shame because, and again, I don't know how much of it was true, but he often spoke about the fact that he was writing a book, making sure that he was writing down all those things. So in the back of my mind, it was fine. I don't until I get to the bottom of my understanding of this bit, I'm not going to really write down too much of it. And I didn't record any of the conversations because I didn't do that. Like when we were just having a one-to-one, that's what it was. It was just a one-to-one. And I can now kind of regret some of that because, did I miss something in what he said? But
Gareth, I did the same thing. I just had my chats with him. I did not record them. And now I'm kind of wishing I would have said, do you mind if I record this? Record. Yeah. And I didn't.
He never mentioned to me who he might have killed. Did he say anything to you, Gareth?
Who he might have killed?
Yeah, there's an ongoing Wall Thornhill murder mystery. We're trying to get to the bottom of it.
No, I knew you were going to bring this up. This is Ben Davidson. Okay, this is Suspicious Observers. We found out that he claims that Wall Thornhill killed someone, and so Matt and I immediately jumped on that, tried to verify it, have found nothing, but it's still a great story.
He keeps his secrets well hidden, unfortunately. We may never know. We got to get Ben on the show.
Yeah, well, it clearly wasn't Ben he killed then.
No.
You're right. We've actually reached. I mean, I don't know if you know Ben's relationship with the Electric Universe. It kind of was.
Oh yes. Oh, you do. Okay. Yes. Okay. Yes, I know it was. Like some of the things that Ben came out and said. Like, yeah, I mean,
a little bit rough.
I don't honestly. I like the weird thing is that the way he describes the way he was not indoctrinated, but the things he had to do in order to join the Thunderbolts. He makes it seem like a cult.
They even let me in.
No, but like, well, exactly. My experience is quite the opposite. It's kind of like, and it's not like if your views go against this, then we won't speak to you. No, in fact, Wall quite liked that. I kind of said, no, I don't agree with that.
This
I
isn't
won't accept
settled.
this part. I like this bit, but I don't like that bit, and he was fine with that.
Yeah,
So
we're pioneers in something that nobody understands, like Stephen Smith said. So we're going to get things wrong all the time. Well, not we, but you guys.
Yeah, but I think in that respect, Ben wanted a specific thing and didn't get it, and that caused some sort of friction.
You were the chosen one.
Yeah, I'd
Unfortunately.
certainly say that.
Right. We have reached out to him, and I would love to, hear his side, hear from him, and haven't heard from him yet. So
that'd be great.
And answer our emails.
So,
okay.
Well, yeah. I think Ben has a particular viewpoint and a particular way of interpreting stuff that I don't really agree with.
He believes in like the cyclical flood cycle, right?
Cyclical catastrophism.
Thank
you.
Yeah. Like I'm not against the idea that cycles repeat. I don't have an issue with that. The issue I have is pushing an agenda that it's soon. And it's soon,
doomsday.
and it's soon, and it's soon. Yeah, and you're kind of like, well, how often can you say it's soon?
Sooner or later, you're going to be right, though.
Well, yeah. Until you're not. Like if you keep saying it and you die, then what do you have to? Your children have to keep saying it, and then your children's children. Like, yeah.
So you don't think Atlas 3I is going to end the world?
No, you mean the aliens that are going to pop out the spaceship and invade us? Those
ones.
But
hold on. What if it gets captured, though? It's pretty big, isn't it?
I mean, captured by the other aliens who were watching the aliens invade us. Yeah, maybe. Yeah, no, I mean, his idea
Your
of...
scientists are no fun.
Well, I'm not sure. There's a bit of science fiction in there somewhere.
Yes, says the science fiction writer, Matt.
So
okay, let's get back to
what is gravity? Surely it's not space.
Actually, technically, if you look at it from a modern understanding, it's not even a force.
Not even a force. Yep. It's the curvature of space-time.
But I think it is a force.
I agree with that. Yeah, it's got to be something.
Yeah. I mean, like the curvature of space is an elegant way of explaining it. Like it has, but the problem is that what is it that you're bending? Like you're back to this. There's a thing which we then call space time, which you're then bending. But what is that?
It seems like making real of an abstraction. Like trying to pretend an abstraction is an actual reifying. Yes, thank you.
Yes, reifying. And Wall pointed out that you take two concepts, space and time, reify them and turn them into something real. It's like, how? How do you do that?
Yeah.
Math.
It's some real puzzle factory maneuvering for sure.
Well, I'm sure it has its elegance in terms of explaining, like a lot of things. And fundamentally, I believe it's not possible to create a theory that explains everything. I just don't think we are capable, or that the universe would allow it. There would either just always be another level that would hide beneath it or above it, that would then mean that it doesn't make sense, or parts of it. Not that entirety, but parts of it don't make sense. And I think therefore, what we always try and do is create stories is maybe the wrong word, but it is a way of describing what's going on, an understanding that you can, in a sense, visualize. And some people, I would say, are can mathematically visualize things. They equations are like drawings to other people. And that's fine. I think there's nothing wrong with that. And there's nothing necessarily wrong with having something that elegantly explains phenomena in a way that actually sort of makes sense. The idea that space-time curves is an elegant way to explain why objects orbit around other objects and why you end up with these effects that Newtonian gravity doesn't necessarily always describe correctly. There's nothing wrong with that. But the question is whether that describes really what's going on or not.
Yeah.
I don't know whether that matters, because at some point, like, you have an abstraction on top of an abstraction on top of an abstraction, but like, does it matter as long as it still describes what you want it to? And what you want it to describe is effectively your interaction, your view of the universe.
Your view.
And I think
and then
well,
there's
Go
the
ahead.
pragmatic side of it, and saying, who cares if we understand it? Can we make things work? Can we take the knowledge that we do have, even if it's levels of abstraction, and still make a phone ring, make a gun shoot, make a television turn on?
Because just because you can explain it doesn't mean you can create science based off it or engineering based off it. And also, just because you can explain it, it should also matter if you had to patch it. Which, as far as I know, Electric Universe hasn't really had to patch, even though it's not a complete model. Whereas adding
Definitely not
patches,
complete.
I would like. There's a lot of
Go ahead and
positives to
disagree.
be had. Well, I do disagree. Fundamentally, I do disagree. Like, if you, you know that my thoughts on the Big Bang and the Lambda CDM model, but what you can't deny is that there is an awful lot of rigor that goes into explaining each part of it. You know, there may be gaps, and the model may be running out of headroom. As funnily enough, one of the things I was working on today is indeed exactly that. But if you look at the depth to which those theories go and how it all connects together, that, like, you can't say that the electric universe has that. The electric universe has theories and concepts that work on a very high level, and if correct, fundamentally changes a lot of things. But the depth to which each one goes, no, that's not there. And that's what I've always criticized it for, is there is so little documentation. I would argue that plasma cosmology is the backbone that the electric universe is built off. And fundamentally, when you're talking about the physics of the universe, that's a lot of the theories are based on that. What electric universe does is then abstract that to, let's say, stars, which plasma cosmology never touched. They kept it the same, and I can kind of understand why, because fundamentally you're trying to explain how the universe works at a big scale. You can't necessarily deal with everything, and electric universe attempts to explain everything all at once, but can never achieve that, because that's such a vast thing to go for that it's almost a hiding to nothing. And it's so easy. The problem is, it's so easy to poke a hole in it that people just poke a hole in it and go, look, see, that's
therefore,
pseudoscience. Yeah, and that's part of the problem. And that's why I always felt that the whole, and I know there's some people really like the whole Saturn being the original sun, and that whole partly mythology that sits behind it. But I always felt that hindered the way that people view it, because you either accept it for what it is, or you look at it and go, well, that's a little bit too mumbo jumbo for me. And I think it puts a lot of people, yeah, well, exactly, bollocks. Indeed. It puts a lot of people off. And I think fundamentally what they should have done is separated too. I understand why they didn't. Like, because people are drawn in by the one but the rigor needs to live in that other part. The mythology side is effectively can be used as a scaffolding for the other bit. But you have to start, in my view, with that rigor in the other parts. And that's, I think, where Wald started with it. Like, if you look at some of his original papers that he did when he still did them, you know, that thought and that idea was there. He was building off what other people had done, and building ideas that would make some of the physics that sits behind it work. But I guess because people, and when I say people, like mainstream science just didn't accept it and didn't want to engage with it. It's pseudoscience that becomes very difficult to deal with, and therefore you sort of pull back on yourself, and therefore they didn't, you know, later he never really published more papers. It ended up being his blog where he discussed things, but even those discussions never went to a level that you could go, okay, well, I understand how that works now. And that was my frustration when I first came across the electric universe. Was I looked at some of these ideas and I thought, oh, that's brilliant. That's, you know, that's a completely different way of looking at it. How does it work? And then you're like, well, where's it written down? Where can I find some what? So that started my journey looking at Hannes Alfvén, who's sort of the pioneer behind the well, I mean, plasma cosmology is his essentially his baby, although he didn't name it that. It was Pratt who named it later on. But essentially, a lot of the foundations of what the electric universe is built on comes from the work that Hannes Alfvén did. And even when you look at his work, the irony is the same thing happened. The same, like, the fact is that he is a Nobel laureate. You know, he came up with, not just him, but he was a large contributor to magnetohydrodynamics.
Right.
A way to simplify the calculations when looking at plasmas. But as soon as he'd done that, he obviously also realized that, okay, in order to do this, what I'm doing is abstracting away the microscopic part of it, those charges that are moving, and that movement of charge actually gives you the dynamisy of what happens inside of it. You get the double layers, you get, you know, the phenomena that occur, you get movement of charge. It becomes a living thing. And the beauty of the way that Hannes Alfvén sort of described the universe is this idea of cells. And not cells as in living things, but effectively pockets of things that exist within, like closed systems that interact and can interact. There can be boundaries between different cells. They can interact with each other, but most of the time, most of the material in one cell stays separate to the other one. And that's very much how I see the universe as well. When you look at it, at a large scale, I think there are these connections that are made between different parts of the universe, but they all run in these self-sustaining chains, and
like cells,
like cells,
like
yeah.
cells.
But they're like when you look at his description, his explanation for the aurora, and then the solar. I don't want to call it solar cycle because it's not the solar cycle, but he had like like his galactic circuit, but he had a solar circuit where effectively you'd have plasma moving out in one direction and back in through the sheet at the edge, and it's that interaction between different cells. So the solar cell interacting with the Earth cell, which creates the aurora. And when you look at his diagrams, the way they sort of connect. That's very much the way I see different things connecting at different scales, and I think that repeats, but they're all in sort of closed loops, and that's one of the frustrations. But that's one of the frustrations I had with Wall in particular, when you know, asking. His idea is very much that everything is connected to everything all at once, and I was like, well, okay, well, what drives it? Where is that mechanism? Because if you're gonna go with that idea, there has to be some, let's say, batteries may be the wrong word, but you need some power source that drives it. Yeah, well, and I suppose you could argue in a galaxy we do see that there is a central engine in the galaxy, but in the electric universe that's a secondary effect. The main effect is this current that connects all things together, but there's never really an explanation of where that current connects to, from what powers or drives it. It's left to
I think the answer is that we don't know, right? I mean, that's what Wall always said. We just don't know.
Well, yes, but that's a very convenient answer, I would say. That's like
I have a different
you're abstracting it. But like when
I have a different answer.
Go on then.
So someone in one of the forums, basically asked that question. That was one of the first questions I had. But to me, I say, where does it come from? Where does it go to? Is the same question or the same answer. Every atom, if you look at it, is its own power source. If you take the basic model that we accept now, that you have electrons orbiting, that is the power source. So anytime you have atoms, that's the source. The source of all the Birkeland currents are the individual atoms all the way around it. Now,
yes and no. I would actually argue that based on that idea, it's back to this idea of closed loops. And that's sure. when you look at the way, for example, Peratt describes the formation of the filaments, and the way that Alfvén shows the diagrams that connect filaments across each other. And in Peratt's book, the Physics of the Plasma Universe, he has this diagram, which is actually where I did the video of the filaments at different scales. I forget what I called it, but the one more recently in Russia, where they'd done these experiments and looked at the structure of the filaments, and actually saw that they don't create just one discharge. There's this very complicated network of filaments.
Very.
Yeah, and there are return paths in each of them. They're loops. Like you end up with these loops that create and that interact with other loops. The energy, obviously, in the discharge in those experiments is pushed in one direction. But thinking about Ampere's law also got me thinking, well, what does that do for a filament? If you consider, just ignoring that filaments are not necessarily straight, but if we just assume a filament is a straight connection from one side to the other, then effectively the longitudinal force component of that means that if the filament is traveling in one direction, that means you have charges spread out across an entire length of this filament. Obviously, those moving in the direction of the current at one end are going to push the charges along in one direction. There's like the force pushes. But equally, on the other end, there's almost like an opposite effect. So you end up with this process when you consider, and these are not necessarily massive forces we're talking about, but on a cosmic scale, when you add them up, as long as you can then, if the current leaves at 90 degrees at the end and comes back, which I know is a bit of a simple abstraction at this point, but essentially you can then almost create like it's not quite a self-pump mechanism, but it's like a more efficient, the charges have to effectively push less because of this force, the Ampere's longitudinal force, that helps them in one direction. Admittedly, at the middle, you're going to get sort of a compression, where the forces act against them. But essentially, you end up with this sort of concertina effect, and then pulling apart effect as they come in and out at the end. Now, obviously, you have to have a closed loop, but and we're dealing with electrons in this case.
Right. Well, so a couple of things. Longitudinal force, for those of the people that don't know what a longitudinal force is, think of a slinky that you pull out and then you squeeze it and let it go. So it's compression, refraction, compression, expansion. It just in simple terms. But Gareth, I'm going to hold you on something right there. With that longitudinal force in that loop you're talking about, there is no movement. That doesn't cause movement. An electron's not moving because of a longitudinal force. All it's doing is this. So, I mean, are you saying this is movement?
No.
Because it's not moving from one end to the other.
Okay, so I'm talking about Ampere's longitudinal force.
Oh, maybe I don't understand
in
the
Ampere's
intricacies
formulation.
of that.
So in Ampere's formulation of the forces between charge, so his law explains the magnetic attraction component of two lines of charges flowing in the same direction being attracted towards each other. But part of that also reveals that between charges that are traveling in the same direction, there's also a longitudinal force. They push on each other. Yeah. And that's
what keeps them
like
moving.
No, this is
Are
additional.
Are they also doing this as they move?
No. Like, I mean, they may well be, but essentially what you're dealing with, the way he looked at it, he cut the current up into current elements. And what he said was that different current elements that travel in the same direction still exert a longitudinal force on each other. It's like a repulsion. Imagine two charges are going to repulse, right? But obviously, when you deal in a wire, normally when charges are moving, you completely ignore that. That doesn't exist anymore. As soon as the charges start to move, there's no repulsion between charges. But what Ampere showed is that does still exist. And
it does still
If
exist.
you look at, Peter Grenot and Neil Grenot's, his experiments show that these forces still exist. And that's why the wires explode. And in fact, Neil has done other experiments that hopefully I'll be looking at sometime in the future that show this as well. And in fact, that there is a way that potentially you can extract energy from these that we're not necessarily utilizing.
That would be amazing.
Yeah, I mean, how much it is, but like the fact is that this, and if you look at Ampere's work, it's irrefutable that this force exists. Now, they try and explain it in more conventional terms, but like the idea is in what Peter and later Neil did is that you can actually measure the size of this force, and this force is measurable. It is a real force that exists on current elements. And therefore, if we consider it at a cosmic scale, those forces have to still exist. And therefore, the idea when you consider a massively long filament is that those forces exert itself, and especially considering we're dealing with instantaneous force at a distance, albeit it falls off with distance. But that means that you end up with this effect that those charges on one end are going to be pushing the charge on the other. Now, obviously, the biggest effect you're going to feel is at the two ends of the wire, because there's nothing ahead and there's nothing behind pushing those forces. So there is an effect, and I still need to try and think of the best way to work through what effect that might have on filaments. But I have a deep suspicion that this might create, it's not going to drive itself. It's not a perpetual motion thing, but it reduces the energy requirements for the movement of the charges at those points. Now, obviously, you do need a return path, and like no energy is free, but you're essentially creating a system that will allow the charges to flow throughout that channel with a reduced energy cost, in my mind. But again, I haven't really looked at this in enough detail to do anything on it.
What about something like that? What about if the filament path that you're describing right now is that guy? Is just that guy? That would be the filament path. So is it looped? Is it connected in the end? Absolutely. Goes right through the middle, comes out, forms another one. Now, I realize that we haven't necessarily seen a cosmic level sized toroidal shape, but it doesn't mean it's not out there.
No. But in Ampere's formulation, it's angle based. It's not to do with whether or not the charges are flowing in it's very much the angle at which the current elements are flowing.
Okay.
So that's why when you look at the explanation for when you bring two coils next to each other, which should create two magnets that repel, but in fact they attract, when you break it down, each loop you would decompose it into a series of current elements that travel in effect in a loop in opposite directions, and you then calculate it for each one of those current elements, not the entirety of it. And when you break it down, what you see is all those components in this direction disappear, and it leaves just the current that flows in a wire, which is why you end up with an attraction, because two wires flowing in one direction attract. And
How
that's
big
the
is a
beauty of
current
his math.
element? How
Well,
big is a
it's
current
an
element?
well, again, if you're going to the smallest level, then you're into the territory of Weber. So Weber took Ampere's formulation and took it to the next level, where he, rather than it being a current element, he started to look at individual particles. So that's
Okay.
your question about magnetism. The Weber very much looked at how magnetism can be explained using the idea of moving charges. So
right.
I covered a little bit of his work ages ago, but that certainly, and I think some of his ideas are also used to explain it nowadays. But he used Ampere's formulation to actually create equations that would act on individual particles, not individual current elements.
Okay. I two things real quick. I just got the 10-minute warning. And secondly, I need to go back about 5-10 minutes into our conversation. You talked about how Alfvén talked about cellular structures or possible cellular structures in space, and that it was scalable. I cannot emphasize how much that is absolutely scalable. There is a word called amphipathic, and I had to look it up because that's not a word I use every day. But it deals with amphipathic deals with the relationship of molecules. And if my right hand's a molecule, my left hand's a molecule, it says that one end of the molecule is hydrophobic, and the other head, the other side of it is hydrophilic. And this relationship is exactly cellular membranes. Like if you were to just, take a blood sample, take a skin sample, look under a microscope, and zoom in on the edge of the cellular membrane, it's an amphipathic system. Now, the other thing that's cool about this is, you're going to have molecules next to molecules. And when you look at that, that is actually a double layer. It's a biological double layer. But you're thinking, wait a minute, there's going to be a charge associated with it. Is this the same thing? When we talk about double layers, is the amphipathic the same thing? I think it is. Or it's very closely related. So
Well,
when you say that they're scalable, absolutely they're scalable.
Yeah, I mean, certainly, but that's the way Alfvén saw it, because from the experiments in his lab to the aurora to the sun to galaxies and beyond, that he saw that these systems created effectively cells within which they operate, and then within those there'd be smaller cells that it interacts with, and those of them have smaller cells that they interact with. So it's like repeating at different scales, not entirely the same, but the same mechanisms allow interaction across those boundaries. So yeah,
that would seem to make the most sense. I can't imagine creation or random chance developing a system with different rules that apply to every different situation.
No, exactly. And when you see some of these explanations that things happen at different scales with different concepts, you're like, really? That doesn't make an awful lot of sense to me.
I think when we look into space, we're looking at the molecular structure of something from way down here. That's what I think. I think when we talked about the structured atom with Ito, that nuclear electron he's talking that keeps the protons separate, I think we're talking about galaxies and Birkeland currents.
Yeah, I don't see it quite like that. In my mind, the scales can have different functional operations, but the mechanisms that drive them are the same. So it's the same forces that drive them. You see a similar thing, but they might, because they're at different scales, they might look different. And then
what are we really looking at? I mean, we can see their magnetic field basically. If we're looking through an electron microscope, like what are we seeing for real?
Well, I suppose, but the thing is that when you look at when you look at an atom, I know that Jim was very, very keen on this idea that like the solar
Jim?
system was Jim Wenninger was
Okay, thanks.
a representation of an atom. So where the heliopause would be like, if I remember it correctly, like the electron shell. So
Yeah.
a sort of boundary layer between the two of them.
One of the
But
one of the outer electron shells or inner electron shells.
well,
Well,
yeah, okay, that's
they're
yeah.
same thing though.
Well, but then the problem is, like you're saying, they're the same, but actually, if we look at atoms, and I would agree that we don't see that much about atoms, but like if you were to say that a solar system is the same thing as an atom, I would say no, it's not, because at the center of our solar system is a sun, and around the sun orbits a number of planets. That's not equivalent to what a nucleus looks like. Like, particularly if you're going with Edo's model. Yes, Edo's model is very much that there is structure, solid structure that we can see, and that structure creates the different properties of the different elements that we know, and that makes so much more sense than anything else. But that's not the same scale. So that's my argument, is that the different scales don't necessarily operate in exactly the same way. They have similar rules, and there are similar boundary conditions that occur between
Think of
objects. But
it.
the question is where.
Think
Well,
of
I
it like
wouldn't
the
say a solar system. I wouldn't say a solar system represents the atom. I would say it'd be more like the whole galaxy, and that the solar systems are component parts of the nucleus.
But even in that
Sure.
analogy, if you're going with a galaxy is an atom, then we see different types of galaxies, which well we don't see that in terms of atoms. Atoms grow larger, but we know that the constituent parts are the same. Like we can break an atom down into fundamental parts, and the smallest part that we know of is the proton. And we know that, and we can fire something at an atom and cause it to disintegrate into smaller chunks that we can identify. I don't think we can say the same for galaxies. Galaxies, we know, and I suppose you could
I
argue
think we can.
that we don't know because we'll not be there. But yeah, we know are composed of millions and billions of stars. That's fundamentally different to what we know about the atom. So I would say
Well,
that.
Sure. The other thing is you can think of it as the organs in your body. They all have, similar boundary
Yeah.
conditions, but they do different things. So a
Yeah.
solar system, in your model, a solar system might be like a spleen, or you would have pancreas and a heart and whatnot. And
What are the chunks of proton made out of? When we blow
That's
apart
actually
the
a good
protons,
let's
what are
finish
those
with that.
chunks of proton? I think that's where your galaxies are.
I so that the whole thing, what happens at a subatomic level, is an interesting discussion, because I think part of the problem is, again, it's how we interpret data. And when you look at
Yeah.
the collider experiments they do, I kind of get the impression that actually we are jumping the gun a lot of times in terms of what we think, because it fits the model. That data we see, that energy level, that must be this. But
Yes.
but is it always that? And therefore, like the idea that the proton is made up of quarks, and there are 3 quarks in the proton. Like, fundamentally, we've never seen a quark on its own. All we see is the fact that when these collider experiments happen, that there are these traces that hint that is
1 minute.
possibly it is composed of something else, but I don't know. Who knows?
Well, we're big picture here.
But I think fundamentally, one of the ideas I kind of am toying with is the fact that for example, the electron can take on different roles that we are misinterpreting as different particles, but actually it's the electron in fundamentally different environments that creates a different signature. So a heavy electron at different energy levels. And there is interesting evidence, because you can extrapolate it down to the nuclear electron. And I think it fits some of the data that Edo he wants a different direction, but I kind of feel that this is a better direction for the understanding of the electron. And I equally think that potentially also applies to the proton.
Yep.
We should put you two together.
We're going to pause. We're about to lose it.
A few moments later.
I have to. You're an Englishman.
Yes.
Are beans and toast really a menu item?
Well, it depends what you call a menu item. Do people eat them? Yes. I don't personally like beans on toast, but yes,
So,
people do.
The reason I ask is that I watched Mock the Week, which is a game show
I know.
there. Watched the whole series, loved it. Someone made a joke about eating beans and toast, and I'm like, that's a thing? So I tried it. I've actually had it for breakfast twice this last month.
It's often like if you go out for a full English breakfast, you often get, but nowadays, because not everyone likes beans on toast, they'll give you baked beans in a little pot with your toast. So if you want, you can put it on your toast.
Yeah. That's what I did.
But that's a bit like Marmite, isn't it? Like it's an acquired taste. I would say baked beans on toast is a fairly common thing. Like it's not an unusual thing, but like it's not something that you would have that often. And often it's like you'd have something else with it.
What's a jumper?
A jumper is a what you call a sweatshirt, isn't it?
I gotcha.
And trousers, not pants. Pants are what you wear under your trousers. God's sake.
Right.
Use the right words.
Exactly. I was watching, like I said, Mock the Week, and they kept using pants, but contextually, I could tell that they were talking about underwear, what we call underwear.
Yeah.
And I'm like,
yeah.
Why are they talking about pants? Because, pants are the outer garment for us idiot Americans. But they kept making jokes about pants, and everyone would erupt laughing. I'm like, why is that funny? But I know, but cousins across the pond and separated by a common language.
Yeah.
So, Gareth, you've been looking into all this for some time. What's your big picture view? Is space electric?
Clearly, space is not electric because what's the definition of what space is? I know I'm getting a little bit pedantic here, but fundamentally, I would say that the universe is plasma. I think it's probably a better way of saying it. It's and therefore the forces that the plasma feels that is exerted on them are accentuated by electric fields. Even if there is, I mean, we're back to the discussion on fields, but essentially, my view would be that the universe is shaped by electric and magnetic fields. That the structure that we see comes from, and I still think there's gravity. So gravity is absolutely still there. So gravity, but a big driver in terms of the structures that we see, the filaments, even to the formation of galaxies and stars, are partly down to electric forces and magnetic forces that create the pinch effects. And I think, in particular, looking at Alphane's work, the double layer is something I think is fundamentally important to understand in that bigger context. And it's interesting because when you look, even, and this is part of the problem of when you try and create an alternative theory. So one of your questions at the beginning was, well, what do you think of an electric universe? And I was like, well, if you compare it to the Lambda CDM, it's such a well put together theory that ties so many things. You might not agree with all those things, but the way that it's structured, one thing builds on the next, which builds on the next, and there's evidence for this, evidence for that.
Well, so is an episode of Seinfeld, but that doesn't make it true.
Okay, but the point is that people spend a lot of time developing these concepts, and the biggest problem that I see in a lot of it is how you interpret the data. And the problem is that even something as simple as redshift, you know, you'd think, and even at the conference I was on, people were arguing, well, it's just something you just measure it from. I mean, yes, you do measure it from essentially from the spectrum that you measure. You can work out based on an assumption of what you think it is, how much it's stretched. But what if you can't use spectroscopy? Then you're into photometry, which is a lot of the more recent observations in James Webb's Space Telescope are photometry. And there you're not, because you're looking at essentially broad filters, and you're looking for the dropout, and that dropout tells you whether you think that the Lyman break is, and if that's where the Lyman break is, then you can sort of pin its redshift. But you can only pin its redshift because you essentially what you're drawing. Imagine if you have a spectrum, you have all these lines, a very detailed structure that you can observe. But with photometry, what you're doing is you're taking filters that have a broad range of frequencies that they accept. But you can capture more light, so you can essentially see further. And therefore, what you're looking at is the point at which that filter no longer sees the object you're looking at. And then that essentially tells you the point at which the neutral hydrogen is removing part of that signal, which you would normally expect the Lyman break. And therefore, essentially, because you're only looking, like it sounds like this super complicated thing, but essentially you're only talking about 6 filters essentially that you've got. So you've got 6 points of data that you've got that tell you how much light they essentially receive, and then they essentially put that, or put on top of that, what they think the spectrum might look like. They're very detailed based on their models, and therefore where that dropout, the really sharp dropout, would be in the spectrum. But they don't actually see that, and it means that when you look at the actual signal and the spectrum that they assume it comes from laid on top of it, you realize that assumed spectrum has a lot of interpretation in it.
It does.
Like those dots, from those 6 dots, you could actually interpret in a different way. And that's part of the problem. When you look at a lot of this data, that it almost means that you can, I don't want to say force the results to match the data, but that's essentially what you're doing.
It kind of does.
The model is confirming itself, right? And that's part of the problem. But the problem is also, if you look at alternative ideas, alternative cosmologies, the problem that you come up against is this: in order to break into it, you have to go to almost the same level of detail. You have to break out these interpretation loops and build your own loops to interpret that data. And even within, like, if you take plasma cosmology, you have Hannes Alfvén's idea, you have Anthony Pratt's idea, and
Stephen
the problem is
Crothers,
that
everybody.
Well, yeah.
Scott.
I'm sorry. I interrupted. Finish your thought.
And Eric Lerner. So those would be the 3 main pillars that I would put in plasma cosmology. But, like, for example, Eric Lerner doesn't really use a lot of the ideas that Hannes Alfvén does, whereas Pratt is very much, because Pratt was almost, they work together on a lot of stuff, so they're very much aligned. Pratt takes it like to the next level and abstracts in a different direction. Alfvén, in his later career, worked together with Klein and came up with his own idea with antimatter sort of thrown into the mix. So they take these diverging paths, and that makes it extremely difficult to say that there is one model, because there isn't one model. Like what Eric Lerner does in order to try and make his concepts work is ignore what I think is some of the really important stuff that Hannes Alfvén did. And I understand why he does that, because he's trying to get acceptance. And the part of the problem is that if you want to be accepted and talk about plasma, you have to talk about magnetohydrodynamics. So those terms that Alfvén said, well, we need to talk about the currents. We need to talk about how the charge flows. We need to talk about double layers because double layers are fundamental to understanding how the and learner doesn't talk about those. So there's a difference in terms of the language that they talk, and yet supposedly they're the same model, but they come to very different conclusions. And this, like, if you look at Lerner's model of the universe, it doesn't talk about these cell structures. It doesn't talk about the evolution of galaxies in the way that Lerner did. Sorry, in the way that Pratt did. Like Pratt's idea of galaxy evolution is sort of what the electric universe adopted in terms of the filament structures and how those come together, and it's a very different way of looking at it. That Lerner doesn't talk that much about galaxies and how they work. He very much talks in terms of obviously his plasma and his plasmoids, because obviously he's building the reactor. And I realized when I was at the conference that some of the language he uses, which when you actually sit down and think about it, is all based on the idea that obviously the end result for him is obviously selling his idea of power generation, and therefore you have to be able to seem credible enough to the mainstream, and that means that you have to adopt language that may conflict with some of the ideas that you hold, but I think it limits how far he can take his cosmology ideas. And maybe that's never his idea. His idea is always about making clean energy. And,
I see him as more of a step in the right direction for mainstream guys.
Yes.
But it seems like
he's a halfway house. Yes.
Yeah. It seems like the further you get away from those models, the more your model might resemble reality. Well, like you said in your last video, whatever you think about Walt Thornhill, when asked what would be the result of better telescope technology, his reply would be filaments everywhere. And that's exactly what we see.
Yeah. And the irony is that the way they explain filaments at different scales is different. And this comes back to the idea of fundamentally it should be the same principle. You can't say that filaments form at a cosmic web scale in a different way to filaments that form in a galaxy. It surely must be the same principle.
Yeah,
that was my favorite
lightning.
takeaway.
Or lightning, exactly. Lightning, clouds.
Yeah,
stuff internal.
I love your presentation about plasma. Like, why does it suddenly follow different rules as soon as it's in space? It just doesn't make sense. It should act the same everywhere.
Well, and then this comes back to the abstraction with magnetohydrodynamics, because the irony is that at a stellar level, so when we talk about the like behind me, the clouds that stars form from, they see those as a sort of neutral. There's not much ionized material in them. Whereas when you look at the cosmic web, that is largely ionized material. Yet the mechanisms that drive the formation there have nothing to do with, they have to invoke dark matter to form those filament structures. So it doesn't really add up.
What was that, Dave?
It doesn't add up. What's that?
No, it doesn't.
So what was that, Dave?
It's a gravitational collapse along dark energy scaffolding, douchebag.
Gravitational collapse along dark energy scaffolding.
Yeah. We like to poke fun at Professor Dave. And that, I think, is the first time I've actually said his name in a year.
Now you're going to get sued, too.
I know.
Well, who else got sued?
Yeah. Hey, Gareth, I had one question just as we're kind of wrapping up, sort of. With all of, you have put out some phenomenal product, and if anyone doesn't know who you are, it's See the Pattern on YouTube. Go check it out, binge it. You will not regret it. You'll probably need some duct tape to wrap around your head, because I mean, you've had some presentations that absolutely blew my mind, and I've been in this for years. They were just fantastic. But my question is, what is one thing that blew your mind when you were doing all this research?
I would say I'm not like blow your mind. No, I don't think like the Ampere stuff for me was quite a revelation, because I hadn't really considered that something that Ampere had produced that particularly in something as simple as just a moving current, that there could be a force that effectively we've ignored. We've abstracted it out of existence, and yet it probably actually is there. And the level of detail that he went to prove that is just phenomenal. I don't think I like blown away. It's difficult to. I don't think I'm the sort of person that's often blown away. I tend to be quite calm and sort of meticulous. I mean, the structured atom model for me always is something that to me resonates so incredibly well. I think that the depth to which, and that's not to say it's perfect, because I think there are flaws is maybe the wrong word, but there are parts that still need to be explained. Incomplete. Yeah, that's probably a better way of describing it. But it does a better job at explaining a lot of things than the standard model. Now, obviously, it has massive implications for the standard model, like no strong force and probably, I mean,
nuclear electrons.
Yes, exactly. I mean, there are a lot of ramifications for it, but fundamentally, the simplicity often. Like, I think often what gets me is someone who can describe something in a way that actually you kind of go, that's just a really simple and elegant way of describing it. And often it's that simplicity that is breathtaking more than blown away. I think you kind of look at it and you go, that's so much better a way of explaining something than what we currently have or the way we currently do it.
I like that.
It seems like science should be that way.
I like how you reframe that from blowing your mind to breathtaking, because even though I'm very high energy and I like to be dramatic, breathtaking is definitely the feeling that it's associated whenever I listen to some of your stuff and some of Ito's stuff. It is. It's literally breathtaking. What's really fun about this, and you may not know this, but are the sequence of these podcasts. Ito is going to be right before you. We just finished interviewing him just a few days ago. So in the future, it's going to be Ito and then you. It's going to be beautiful.
We got to get a tag team.
Fun.
Oh yeah, I mean, happy to go on with Ito. I mean, I often talk to him anyway. Not recorded, just
chat. He told us that, yeah. The you two just chat. Yeah. Well, he's in your time zone, isn't he? Just like an hour behind you or something?
It's an hour. Yeah.
Makes it a little easier. When we call him here, we call him here at night, and so it's getting later and later for us, and for him it's early morning, and it's getting later and later in the morning. So that doesn't stop us, because the last time we had a chat, we were on Discord, Matt and I talked to Ito for 2 hours, then Matt joined us and he talked for another 2 hours. And then the next day we did the podcast for another 2 hours.
Yeah,
it was insane.
But if you can get Ito going, he's very hard to stop sometimes.
Yeah, he's fun to talk to.
Yeah.
Yes.
He'll go off on a tangent though, but
a little bit.
This was fantastic.
This really was. Gareth, we really appreciate you coming on with us.
It's a pleasure. I enjoyed it.
All right, we'll see you next time.
All right, take care. Have a good night.
Thank you, guys.
Take care. Bye-bye.
Bye.
Thanks for listening to the Brainstorm with Sparks and Finn. Hope you learned something new or found some food for thought. If you did, take a second to smash that like and subscribe button and consider joining our Patreon to help Sparks and I spread the word. And then join us next time as we explore this amazing electric universe. Cheers!